Hello, and welcome to our panel today. We're going to go ahead and get started. This is an exciting panel to describe to you a workshop that we held last November. If I could have the first slide. And this is, it was the seventh community workshop on achievability and sustainability for the human exploration of Mars. That's a mouthful, so we typically just refer to it as AM7. So I'm going to introduce our panelists to you today, and you can see a lot of us there in that picture on the first slide. Lisa May is the Chief Technologist for Lockheed Martin's Commercial and Civil Space Advanced Programs. Lisa is responsible for leading technology strategy development and is the advanced program's principal advisor for all the CCS technology strategy investments and partnerships. Prior to assuming the chief technologist role, Lisa served as the deputy space exploration architect. And then before joining Lockheed Martin, she had founded Murphy & Consulting to provide systems engineering and management services to entrepreneurs in such diverse fields as nuclear, forensics, space, and transportation technology. Prior to that, Lisa was at NASA headquarters, where she managed NASA's Mars exploration program. Her portfolio of Mars missions included the Mars Sample Return, MAVEN, and the Mars Technology. Next up is Michelle Rucker. Michelle is a native of Anchorage, Alaska, and she's a 34-year veteran of NASA. She began her career in the Houston oil industry, designing downhole sensors while pursuing her undergraduate and graduate degrees in mechanical engineering from Rice University. She began her NASA career as a test engineer at the White Sands Test Facility in New Mexico. Michelle's had the good fortune to participate in a range of exciting projects, such as the International Space Station Environmental Control and Life Support Systems development, supervising spacesuit and extravehicular activity tools projects, ISS exercise equipment system engineering, and Orion and Altair lunar lander test and verification. She currently leads the Mars Integration Group, developing crewed Mars mission concepts. Next up, we'll have Clive Neal. Clive Neal is a professor of planetary geology at the University of Notre Dame in Indiana. He grew up and was educated in the UK, where he obtained his PhD from the University of Leeds in 1986. He moved to the US that year and took postdoctoral research fellowship at the University of Tennessee in Knoxville, where he began his study of the moon through analysis of Apollo samples. Dr. Neal has chaired NASA's Lunar Exploration Analysis Group twice, from 2006 to 2010, and again from 2015 to 2018. He's currently a member of the National Academy's Committee on Astrobiology and Planetary Science. Clive is passionate about NASA's returning humans to the moon and beyond in a sustainable, economically beneficial, and permanent way. In 2015, he received the NASA Wargo Award for contributions to the integration of exploration and planetary science throughout his career. And finally, we have Brett Denevi. She's a planetary scientist at the Johns Hopkins Applied Physics Lab. She's the deputy PI for the Lunar Reconnaissance Orbiter Camera, science chair for the Lunar Exploration Analysis Group, a co-investigator for the NASA ShadowCam instrument on the Korean Pathfinder Lunar Orbiter, and the lead lunar scientist for APL's Lunar Surface Innovation Initiative. Brett is the recipient of the 2015 Maryland Academy of Science Outstanding Young Scientist Award, a NASA Early Career Fellowship, 7 NASA Group Achievement Awards, and this is the coolest of all, she has an asteroid named after her. Asteroid 9026 Denevi was named in her honor. So with that, I'll go into a little bit more of an introduction of the workshop. If we could have the next slide. Go ahead, there we go. So we held this workshop last November, and one of the things that we were most interested in, as I said, this was the 7th in a series. So we had conducted prior workshops and determined that we were interested in looking at what we could do with NASA's program of record, which is the Artemis program, to enable NASA's plans for future Mars missions. And so we thought about that as we were organizing the workshop, and we broke up into two breakout groups, one for capabilities and one for specifically looking more in depth at ISRU, or in situ resource utilization. If you saw the panel yesterday, you heard some about that. So we looked at several things here as are shown on this chart: the ascent vehicle and lander extensibility, surface infrastructure, rovers and mobility, operational strategies. How are we going to do some of these things? Get in and out of these landers, go from microgravity onto partial gravity. We looked at things like, what are the things we really need to do before we get people there? Priority surface and orbital reconnaissance. Things like lunar resource exploration. We talked in terms of specifically for ISRU, production, beneficiation, I hope I said that right, Clive, and commodity storage. Clive will tell you more about that in detail. Pros and cons of different cryogenic propellant combinations. And we heard a little bit about that yesterday. Do we go with LOX methane? Do we go with LOX hydrogen? And then finally, ISRU-based site preparation and construction. We'll go on to the next chart. We, in order to do this, and we had this over 2.5 days, so it's pretty tough to cover all that in 2.5 days. So we set ourselves some workshop assumptions. One was that we were going to stick to the plan and humans will land on Mars in the mid-2030s. Therefore, we've got to accomplish a lot in the near term. For ISS and Artemis, we assumed SLS and Orion would be transporting the crew, that we'd have the gateway in near a rectilinear halo orbit. We'll have an HLS, or a human landing system, and robotic precursors, including the CLIPS missions. And then we'd also have some Mars precursor missions. We thought that ISRU should be mainly focused on lunar water resources, as that had direct applicability to Mars. We did look at and utilize the output of the Lunar ISRU 2019 workshop, which had been held a few months prior to our workshop, and there is a link that can be accessed in our report. We thought that this was a good basis for the activities required to make the lunar resources available for subsequent Mars exploration. And then finally, we thought efforts undertaken on the moon and in preparation for the first human Mars missions should proceed in parallel. So in other words, we didn't have to do all the things we were going to do on the moon before we started some of the Mars activities. Let's go to the next chart. So at this point, I'll hand it over to Lisa, who can tell you a little bit about the findings of the Capabilities Working Group.
Hi, thank you, Joe. So we went through 85 different activities or functions that the group, as Joe mentioned, there are two, the capabilities and the ISRU. So ISRU is a special case that you'll hear from Clive and Brett. But in the capabilities working group, we looked at 85 activities or functions that we were determined to be necessary for humans to live and work on either the moon or Mars, well, specifically Mars. And we started reviewing those and figuring out which ones would be enabled by Artemis, which ones would enable risk reduction by going to the moon first. And we found that both Artemis and the International Space Station actually could retire a great deal of risk and prove technologies and processes that are going to be needed to send humans to Mars. They either naturally contribute or can be easily modified in order to make their applicability even more direct to sending humans to Mars. There is, as Joe said, a need to develop some Mars-specific technologies that should be going on in parallel, and that we should be looking at retiring risks, proving technologies, and living and working on the moon in parallel with developing those specific unique technologies. Next slide, please. As I noted, some things that we already do in space, for example, at the International Space Station, and things that are planned in NASA's program of record, Artemis, could easily be modified in order to emulate and test operations and crew performance and things that are going to be needed for the longer transit and the longer stay time potentially at Mars. So for example, the gateway that Joe described at the near rectilinear halo orbit at the moon, we could extend crew stays. Right now they're planned to be relatively short, but we could emulate Mars missions, Mars transit durations by having crew stay for a longer time on the gateway. And also the descent to the lunar surface and the ascent back to gateway. And Michelle is going to talk in a bit more about operations, but the process of landing crew on another planetary body and having them perform their functions and return to a rendezvous in orbit, in the case of the moon with Gateway, or in the case of Mars with a Mars base camp or other transit vehicle that would return them to the Earth. And those operations are some things we have not yet practiced. So being able to shake down, if you will, the processes as well as the technologies and have those well in hand before we send humans far away to the moon, far away to Mars, particularly when the return from Mars can only happen at specific times. So practicing those activities and learning about what technologies and tools are needed in order to accomplish them is an important precursor. And then, to say a bit more about risk reduction. Everywhere, the space station, the lunar surface, gateway can enable us to reduce risk. And by reducing risk, when engineers talk about that, it means we are proving out the technology and reducing the risk of the overall integrated system when we actually put it all together and send humans to Mars. So the important note, though, is that simply having humans on the surface of the moon doing their work, doing their exploration, science, and building up a sustained presence is not adequate. There will be crew health, crew performance, and other things that we will have to also prove out on the International Space Station or on the Gateway. And to talk about crew health and operations, I'm going to hand it over to Michelle with the next slide.
Thanks, Lisa. So crew health and performance is something everybody can relate to. There are a lot of, I wouldn't say issues, we use the word issues here, but things that we worry about that we just don't have enough data on. So for example, we have a lot of data on how humans perform in Earth gravity. And with the International Space Station, we've learned a lot about how humans perform in microgravity and almost no gravity. We don't have very much data on partial gravity. So being able to work on the surface of the moon would fill in some of that data gap. The gravity on Mars is a little bit different than on the moon, but giving us one data point sort of in between the 0 and the 1 would be good for us. As Lisa mentioned, the crewed Mars missions are going to be fairly long missions. It's pretty far away to get to Mars and back again. So having that extended duration. Again, we've done the extended duration on ISS. We've done up to 1-year missions on the space station in microgravity. Being able to get a little bit more than we did with Apollo for the partial gravity would help us, safely understand how the humans perform. We're a little bit closer to Earth. We can bring them home again if we think there's any concerns. It might help inform some of our countermeasures, some of the Joe mentioned the exercise equipment that I worked on early in space station. That was instrumental in helping crew remain healthy on the space station for long periods of time. So we don't know what we don't know about being in partial gravity. So there's a lot we can learn being on the surface of the moon. Psychological effects of being far away from home, only being able to communicate with your family through virtual means. A lot of us are sort of learning that now in pandemic times, but there's a lot of communication things we can learn, how to do our extended operations when there might be a little bit, there's not as much of a communications lag on the moon as there is on Mars, but that little bit of communications lag, we can learn a little bit there. There are a lot of surface activities, how the spacesuits perform. In microgravity on the space station, you don't need to walk. You use your hands for your walking because there's not much gravity. On the moon, we'll have to learn how to walk again. So The boots, on the space station, they were mostly just to keep your feet warm. On the moon, we'll have to learn about how to ambulate a little bit more. Again, with the gravity, you're carrying a heavy spacesuit, trying to understand what the limitations are. Can we go on a spacewalk every day, or how much time does the crew need to rest in between spacewalks? So there's a lot we can learn on the moon for crew health and performance. Next slide. And operations, I touched on this a little bit, but as Lisa said, landers coming and going from the gateway will look a whole lot like landers coming and going from a Mars deep space transportation system. So we can learn a lot about just the operations, being able to do autonomous operations, being able to do maybe robotic or remote refueling operations, servicing. We're going to have to do maintenance. It's one thing to bring your equipment into a nice clean lab and lay it on a table and being able to do repairs where you have a whole logistics chain. When you are limited on resupply, and perhaps you have to 3D print a repair part, for example. Learning to do that on the moon, where if something goes wrong, it's fairly easy to get the crew back home again. That's a great way for us to practice how to do that. The vehicle aggregation, but trying to link up all these pieces. We've done that, obviously, with Space Station. We launched it in pieces and put it together, but it was still fairly close to home, being able to do the logistics resupply. I think the number I heard, 120 days is the longest we've ever gone without resupply to the space station. The moon's still fairly close. We can still do some pretty good resupply at the moon, but trying to predict what we'll need, when we'll need it, and figuring out how our supply chains will work will inform what we're going to do on Mars. For Mars, there's not going to be any time resupply. We'll have to plan it based on the orbital mechanics of the planets. It's going to take a long time to get replacement hardware there. So we'll have to have very good prediction capabilities, and we can learn a lot of those things either on the gateway or on the surface of the moon or both. And I will turn it over now to Clive.
All right, thank you, Michelle. Go to the next slide, please. And yes, as Michelle said, resupply is a big issue. So what can we use actually in the location we're going to? And I'm talking here about what we've learned about the moon. And you heard Joe talk about the Lunar ISRU 2019 workshop. We learned a lot from terrestrial mining companies there. But one of the important things for using local resources is sustainability of human space exploration. As many of you are aware, it's 48 years ago this year that humans last ventured beyond Earth orbit and set foot on the moon. They took everything with them, and they left a lot behind because we're taking pictures of them now. So if we could then start to use the resources that we now know that are present on the moon and Mars, we can start to actually not bring everything with us and start using the local materials. But this has implications for sustainability, especially in terms of, you can see on the slide there, this highlighted term reserves. So we know that there's water ice on the moon, and we focused on that as part of the AM7 workshop because there's water ice on Mars. But elevating this subset of resources to reserves has economic implications. And in terms of profitability, for actually creating opportunities for the commercial sector, creating jobs, creating a new sector of the economy, because that's a return on taxpayer investment in space agencies that will allow sustainability. So we need to go good old-fashioned geologic prospecting to understand how much is there, what form is it in, can we actually extract it and use it? These are important questions that we need to know as we start to map out what sector, what part of the resources are actually reserves. And the interesting thing is we went through this exercise at the meeting. The processes by which we define lunar reserves will be directly applicable to Mars, even though the underlying geology is different. Next slide, please. So, and there's the time lag. There we go. So the other thing we learned from the Lunar ISRU workshop is that resource extraction is power hungry. We need to have reliable and sustainable power supplies. On the moon, we can use solar as long as we're not in eclipse. But as you go further away on Mars, the solar is not really an option given the magnitude of power that's going to be needed. So talk about scalable nuclear power systems was discussed a lot, and the moon would be an ideal test bed for that, to actually prove these different power options out before we actually get farther away and out to Mars. So these scalable nuclear power systems is going to enable ISRU and would be a valuable feed forward to Mars. Next time step, please. The other thing that we needed to focus on at this time was feed forward technology developments. Autonomous capabilities are important because of the time lag. If you're doing operations from Earth, we know that well with the Mars rovers. But there's also these. If you're doing ISRU on Mars, being able to have systems work autonomously is very enabling for preparing for the arrival of humans, so that they can arrive and be in have good life support capabilities, so on and so forth. Again, you can do this on the moon, and we'll have a direct feed forward to Mars. And again, learning to operate and maintain ISRU systems on the moon has direct applicability to Mars, because a lot of the unknown unknowns in operations, maintenance, etc., can be tested, can be mitigated much closer at home. And then finally, the materials handling. If we're processing these local resources, the materials handling and water cleanup and purification becomes very important. The further away from Earth you get, the more remote you are. Again, tested in our own back garden on the surface of the moon is something that would be very enabling. And for the last part of this presentation, I'm going to hand over to Brett.
All right, thank you. Next slide, please. So one of the questions that we considered in terms of how lunar ISRU can and should feed forward to Mars was the specific propellant, and whether you need to use methane at all locations or if hydrogen can be incorporated into the system. And so this is, it sounds like a detail, but it is an important thing that needs to be considered up front, because it will help to define the overall infrastructure and power requirements. For Mars, LOX methane can be derived from in situ resources, because you can generate carbon from splitting atmospheric CO2 and then combine that with hydrogen derived from water ice to form methane. But this is, of course, not something that you can do on the moon unless you bring your own carbon with you from Earth. So you could instead consider a LOX hydrogen propellant. But there are advantages and disadvantages to each. You can see some of the information about both on the right-hand side there. For example, hydrogen is more efficient, especially for nuclear thermal propulsion, but it's harder to store without boil off, and you would have to design storage for something that boils at a temperature of 20 Kelvin. So there are important reasons to use each propellant, and both should be considered viable options for human missions to the moon and Mars. But in terms of building systems and heritage that can directly feed forward, there would be value in using the same propulsion system in both places. I think you can add the next time step there. And what is developed for that system, how ISRU proceeds, and the overall lessons learned will be strongly influenced by this propellant decision. So when making that decision, the broader picture of solar system exploration should be considered rather than just a single destination. Next slide, please. There we go. And the same goes for a lot of other decisions, including what develops in terms of the regulatory environment. There will be legal ramifications for commercial resource extraction activities and important precedents established at the moon that will inevitably carry forward to Mars. So keeping that big picture in view is important. Next slide, please. In situ resource utilization also extends to construction and using the local materials to develop a supporting infrastructure that includes things like roads, landing pads, radiation, and thermal protection. And in particular, one of the big concerns is rocket plume interaction with the surface, where you can eject particles from the surface at extremely high velocities, up to 2 kilometers per second. And these can have very severe sandblasting effects on any assets that might be positioned nearby. Or you can even end up creating a crater where you want to land. So building up berms to protect assets or a landing pad to protect the surface and prevent this interaction of the plume with particulates are obvious ways to mitigate some of these issues. And although there are environmental differences in terms of what the surface is made of, the atmosphere, etc., what you learn at the systems level for construction using local materials on the moon will directly feed forward to Mars. Next slide, please. And so now wrapping up the overall high-level findings in terms of how we can leverage the Artemis program to enable human missions to Mars. First, the Artemis program, including surface operations at the Artemis Base Camp and what is done in cislunar space at the Gateway, has overall very high feed-forward value for human exploration of Mars. Next, in terms of going to the moon and Mars in a sustainable way, we need to understand how we can use the local environment. And we especially need to know if the resources on the moon and Mars are in fact reserves that can be used to enable humans to survive and thrive at both locations. Focusing current exploration goals on understanding this question will be key. And then finally, learning to operate and maintain ISRU systems. And I'll take the liberty of broadening this beyond ISRU systems to be more general, that learning to operate and maintain all kinds of systems on the moon will uncover unknown unknowns and provide important system level knowledge that will directly inform our long-term planning for Mars. And with that, I will turn things back over to Joe. Thanks, Joe.
Thank you, Brett, and thanks to the whole panel. That was a really good and informative overview. I want to kick this off with a few questions, and then I think we're getting some questions coming in from the audience. So I'll start off, I think I'll go in reverse order. So I'm going to start with you, Brett. As a scientist who's worked on the lunar imaging from orbit, can you comment on what could be done to help us locate resources on both the moon and Mars from orbit? Is there something you could say about specific instrument technologies that are coming along that might help us do that better?
So right, I do focus a lot of my work on remote sensing data, but in this case, I think really the next step is to stop being in orbit and really get down on the ground and start digging in the dirt and understanding what is actually there in the surface. Because we can do a lot in terms of looking at the surface or even the subsurface with understanding the hydrogen content, or some radar technologies can look at the subsurface water ice content, but there are always ambiguities there and things that we cannot know until we actually are on the ground drilling, coring, pulling up materials and doing that very local prospecting in terms of what you have at the scale that would be relevant to humans and ISRU systems actually operating on the surface.
So something like Viper then.
Yeah,
really
Viper is a critical first step, but we need to continue on from there with what we learned from Viper.
Yep. Got it. Thank you. Clive, I've got one for you here. You spoke a lot about how we need to understand whether we have resources or whether we can count on reserves. Can you discuss a little bit more about how that can be established? What do we have to do to make that happen?
Well, following on from what Brad said there, we got to get to the surface and understand in the local detail of what is there, what form it is in. Can we actually extract it? Can we actually process it and store it? So if we're dealing with the water ice, we know on the moon that water ice is not pure H2O. There are other contaminants, if you like, but that's important for it's important to understand, because those contaminants down the road could be a resource. So understanding how much is there that we can actually extract and use is going to dictate the architecture of what we put together to go to the moon and then Mars. So it's critical to do that now, but in both planets. And again, trying to identify those reserves, it then opens up possibilities. It implies commercial participation, because that term sort of includes profitability. So it's to me, this is critical for sustainable moon and Mars human exploration, because involvement of the private sector, it will give you that return on the taxpayer investment by opening up and creating and broadening the cislunar economy to a lunar Martian economy many years down the road. But we've got to start somewhere, and we start at the moon. And again, what we learn at the moon is directly applicable to how we go about things at Mars, especially in terms of water ice.
Okay, hey, thank you. That's great. Michelle, I got having all this now that we've looked at and our output from the workshop. When do you see NASA committing to a Mars mission with humans? We talk about burning down the risks using Artemis. What risks do we need to better understand to make that commitment?
So the policy right now is humans to Mars in the 2030s. We want to try to get going before the 2030s are out. The folks that I work with in the Mars team joke that we're always perpetually 30 years away from Mars, and I think we've finally broken that 30-year ceiling. We're getting a little bit closer now. So this is 2020, halfway through 2020. So 2030s is coming up on us pretty fast. Those of us who worked some of these big programs, you know, this takes a long time to design, develop, test, and certify hardware. So we're getting there. I always say, if you try to do Mars starting from scratch, it's really hard. But the key point is we're not starting from scratch. So a lot of the systems that we're developing for Artemis, a lot of the systems we've already developed either for space station or all the way back to space shuttle, a lot of those systems are directly extensible to being able to go to Mars. So we're not starting from scratch. So let me give you some examples. Orion, you know, we always used to worry about the re-entry coming back from Mars. Now with Orion, all we have to do is get back to cislunar space, link up with Orion, and Orion, so we just check that re-entry part off of our list. Orion's got that covered. Logistics and resupply. We have to take a whole bunch of stuff with us to Mars. You know, back when we had the space shuttle, you could launch a lot of stuff, but it was a really big payload capacity. With the commercial launch vehicles now, we can launch faster and you know, more regularly, so we can get a bunch of stuff up into orbit, aggregate it in cislunar space. Gateway is another example of how we would be able to use that asset to do an aggregation. So we don't have to go build something that's already going to be taken care of for us. So we'll be able to get the logistics we need. We'll be able to aggregate it. All of the crew health and performance stuff, the exercise equipment. I saw a question in the chat panel about circadian rhythms. We've learned a lot about how to keep the crews healthy and as normal a day as you can have being in space. Things are obviously much different, but trying to make them comfortable. We've learned a lot from space station. We'll learn even more from Gateway, and then of course when we get to the surface of the moon, we'll learn a lot then. So we're shooting for the 2030s. Everything that we're doing from space station all the way to the surface of the moon, that's all feeding into our plans for Mars.
Super. On the space station, have they, I think I'm right, they've done some work in terms of the circadian rhythms with lighting and using lighting to help adjust and things like that?
Yeah, so on space station we had crew quarters that were developed so that it's sort of like a private bedrooms, nothing luxurious. It's direct space, so it was a tiny little closet. But just being able to go into your own space and close the door, but we're still learning a lot, even on space station, about ventilation. I was involved early on in crew quarters with arguments where some folks wanted chilled air, they wanted to sleep at 50 degrees, and other folks like it a little bit warmer. So trying to design a system that's flexible enough to be able to take into account different personal preferences. Ventilation, noise, this was kind of a funny one. Those of you who worked in aerospace know we get lots of requirements. So the safety community wanted a requirement for a certain decibel level for the alarms, because if you were asleep and something went bad and an alarm went off, you want to be able to hear it. But the crew were trying to sleep, and so these nuisance alarms would go off that weren't necessarily dire emergencies, but it was just it was a nuisance. Just, hey, filters getting clogged, you should go think about replacing the filter, that kind of thing. And so we had to kind of learn how to balance those things. It's the things that the engineers writing the requirements think they make sense, but then when you actually get into hardware and you put humans in the loop, trying to figure out how that is actually going to work in practice, turns out you need a lot of practice. So we've gotten a lot of practice on space station. We'll get a lot more, like I said, on Gateway. Gateway's a little bit more deep space environment. On Earth, you're going around, you're seeing sunrises and sunsets over and over again.
And it's right outside your window, right?
Right. So being in the deep space environment will give us a little bit different experience. So yeah, we're pretty excited about the Gateway and the Artemis program.
Great. Lisa, I'm going to come to a question for you, but since we talked a little bit about Gateway there, and I'll throw this one to both you and Michelle, there was a question from the audience about Gateway and the fact that we're really not talking about using it in the 2024 lunar landing now, but I think it's still important for the sustainable longer term. So could both of you, Michelle just spoke to some of the things we'd like to do on it, but I guess the question is, how are we going to do 24 without Gateway? And then what are we going to do beyond that?
So Gateway, like space station, is planned to evolve from a small halo, which is a small human element, and a power and propulsion element that the Orion crew capsule can dock to, and then the lunar landers can depart from and return to. So the initial Gateway is, in fact, not even the complete concept that NASA is planning. And it's really even though the initial Gateway would serve as a proving ground for some technologies to go forward, we're anticipating an international participation in a much fuller system. The person who asked the question is referring to the fact that the human lander system that is planned to go in 2024 could potentially dock directly with Orion, as opposed to docking with the Gateway and having Orion dock to the Gateway and the crew transit through the Gateway into the lunar lander system. So it's an alternative. It's an alternative that may make sense for the first lunar lander. It's an alternative that may take into account schedule and other considerations for this initial Gateway. But the long-term plan still remains to have a fuller, larger Gateway that can provide this risk reduction for forward to Mars and a place for the crew to return from the lunar surface and all of the other things that we've been talking about.
Thanks for that. Well, let me go to the other question I had for you. You've been looking at Mars for a long time from your prior work there at NASA. And you've been to, I know, a lot of our workshops where we've talked about long poles and things like that. I think there's another session that's covering the long poles here at the conference. But what do you see as the longest of the long poles, I'll call it, for an initial human mission to Mars right now?
So as a technology person and as a systems engineer, I have I have a whole laundry list of things that I would like us to see mature some of which are already exist and need to be matured, and some of which need to be demonstrated and proven. So there's a long list of items, and the good news here is that NASA has a technology program of record to cover technologies in the area of going and transport, to landing technologies for different planetary surfaces, as well as technologies needed to live and explore those places. So NASA's program of record is retiring a lot of the risks. I mean, the poles are, some of them are quite short, and they're getting shorter thanks to the Space Technology Mission Directorate and the Artemis program. The one that I, from my experience in the Mars program previously, the one that I would say is likely to have the most surprises as we retire the risks and mature the technology would be landing large systems on the surface of Mars. Those who recall the 7 minutes of terror, which we're about to experience again with the Perseverance rover. It is, Adam Stelzner is talking later in the EDL panel this afternoon. I believe the quote is, when you look at it, it seems crazy. And so, knowing that those tests and that development was a lot more necessary, not more than anyone particularly anticipated. Our experience with the Mars exploration rovers in the early 2000s taught us that parachutes don't always behave on Mars the way you think they will. So coming up with the architecture and the systems and testing and proving those with large cargo like a crew lander is, I think, going to be the thing that will require the most investment, and as I said, probably has the greatest opportunity for surprise. As they say, the difference between theory and practice is much greater in practice than in theory.
Hey, that's great. Thank you so much. There's another question that's actually a good lead-in to a question that we got from the audience. What are the accumulated risks in landing a crewed spacecraft? And this is a spacecraft with crew. I have a hard time sometimes when I say that. It doesn't sound like it means to be. But landing a human crew with a spacecraft on a celestial body. So what are the accumulated risks in doing that? Anybody want to take a crack at that? I've got some thoughts too. I'll lead off.
I'm game.
Go for it. Go for it.
I'm game. So so I agree with everything that Lisa said, and I would add something. In addition to the crew landing risks, you've also got to get them back home from Mars, right? So to date, all of our Mars missions have been one-way affairs. We've never tried to leave Mars. We've been pretty successful. We've had some hit and misses, but we've been pretty successful at landing things on Mars, but trying to get something back off of Mars and then back home again. So the ascent vehicle, Clive talked about potentially, utilizing Martian resources to be able to make return propellant. That's a really cool idea. What that means, though, is you have to land some stuff in advance and then fill up your vehicle. In other words, you can't land in your vehicle because the tanks may not necessarily be full when you land. So there's the timing sequences of trying to get everything in place before the crew gets there. So landing, like Lisa said, that is a huge risk. The cumulative risks, you've got to integrate your payload, whatever it is that's on your lander. So it's your crew or your habitation, your rovers, whatever is on the lander. That all has to be integrated on Earth. Launch, that's a heavy lift. So that's one risk, just trying to get this heavy lift into space. If you need to top off fuel, there's risks involved with, in space propellant refueling. Then you got to get it to Mars. It's a long journey. Things can happen, sensors go bad, things like that. Then when you get to Mars, you're trying to get there as fast as you can. Now you got to slow down, and then you got to re-enter. There's just enough atmosphere on Mars. That's what the 7 minutes of terror is about. You've got to be able to slow down and land. Unlike on the moon, where there's no atmosphere, so it's a different type of a landing system. With some of the robotic payloads that we've used in the past, we've used airbags and parachutes and so on. For a human-sized lander, the payload's going to be much bigger.
Right.
The largest thing we've ever landed on Mars to date is Curiosity, which is about 1 ton. We're estimating at least a 20-ton payload capacity to land the humans with even just the minimum amount of stuff that they would need is still going to be about 20 tons. So it's 7 minutes of terror, but on a bigger scale. Once you land, as Clive pointed out, power is a big deal on Mars. You're going to have to switch over to a surface power infrastructure, and then go all of the hazards that we've always talked about on Mars, the dust storms and the extreme temperatures, the atmosphere. But then it's time to come home, and now you've got to push the button on your ascent vehicle and hope that it goes. And it may have been sitting there for a while, right? Depending on how long you ended up staying on the surface, you want to push that button, and you don't have a big test stand. You don't have that whole crew that we have at the Kennedy Space Center to make sure that it's topped off. It's just you. You are going to be the maintenance crew for that thing. So yeah, there are a lot of accumulated risks. We know what they are. It's a matter of integrating all those systems together, having the right processes in place, the right tools, and as much as we can, make it as simple as possible so that you have fewer things you have to do when it's time to either land or to come home again.
Yeah,
that's a really good point. I still remember as a kid holding my breath when the Apollo missions were ready to take off from the moon.
And one other thing about Mars is you can only go or come back every 26 months.
Right.
Because we launch missions when we're catching up to Mars, or Mars is catching up to us, and so the opportunity, the risk of taking off from another surface, like Michelle said, you're your own ground crew, you're your own launch team, you're everything. It has to go on time.
Right.
The planets do not wait for you.
Yeah.
So the additional factor of precision to a point, timing of getting off of Mars and rendezvousing with that ride home is another risk, and something that part of the up and down operations from Gateway to the lunar surface can help us practice.
Yep. No, that's a real good point. Anybody else on that one?
Yeah, just a quick point about Apollo 11. Having the humans in the loop in Apollo 11, they landed with less than 30 seconds of fuel remaining.
Yep.
So having a functioning human, as cool, calm, and collected, was critical for achieving that first landing. When you're taking the humans out to Mars, they're in microgravity for much longer. They're in the harsh radiation environment much longer. So this idea of crew health that we talked about at the beginning is critical for that first landing, in my opinion, because you've got to keep them sharp. You've got to keep the crew aware, and they've got to be ready to take over for those unknown unknowns, putting a human lander down and landing the first humans on Mars, having the humans in the loop ready to take over in case there's an unknown that we need to react quickly to. Then I think that becomes very important, and that is the crew health aspect is very intertwined with landing on a celestial body, and also getting the humans back.
Yeah, and I was going to point out on Apollo 11, it didn't hurt that he was a Boilermaker.
We won't talk about that.
I got another one here from the audience. So this is from Michael Helton, and he asked about our workshop. Did we consider using the moon to set up a first station that we would, use as a sort of a precursor for the Mars outpost, using the same resources and procedures? And I think the answer to that is, in essence, that's what we're talking about with using Artemis as the current program of record. It may not be the complete lunar outpost before we actually get going to Mars, but we'll certainly be pioneering and proving out a lot of those operations, as folks have already mentioned. But anyone else want to take another aspect of that one, maybe? Okay. I think the key thing
I'll have a crack at it. I'll have a crack at it. I mean, because it's exactly what we've been talking about is using the moon as an enabling asset.
Right.
Talking about reducing risk. I want to see humans on Mars. I hope it will be within my lifetime, but it certainly will be in my grandkids' lifetime. So, but I just don't want to see flags and footprints. I want to see the sustainable nature of it. So everything we can do at the moon Developing sustainability at the moon gives us a template for developing sustainability on Mars. So the things that we do off planet have got to show that sustainability, i.e. return on investment. So there's a lot of technology development that we need for human space exploration that can be used here on Earth. Apollo was a great boost to the American economy. Yes. So we need to remember that we're building and developing these technologies for looking further out into the solar system. But we really need to be developing those technologies that will be enabling to go further, to go for longer, and to go more safely, so that we can make this multi-planet species idea a reality, because it really comes down to looking at that return on investment back to society down here, so that we maintain the support not only from the decision makers, but also the general public.
No, that's well said. Well, listen, we're coming up on 5 minutes to go, I think. So I wanted to throw out one more kind of general round robin for the panel. Everyone, please give me your answer to this one. So we've talked on this workshop that we described to folks, we've talked a lot about how we can use the moon to prepare to get ready to go to Mars. What element or activity do you feel will contribute most to our understanding of the issues facing future Mars explorers? And let's go in reverse order again. I'll start with Brett.
Okay, well, I think I'd like to just jump off of what Clive just said in terms of learning how to do things in a sustainable way. And so that means sustainable in terms of budget and the ways we incorporate commercial activity and develop an economy. It means sustainable in terms of developing political support, support from the public, and developing a program that can continue to build on itself and make important steps forward, not, as Clive just said, flags and footprints. So, and then it also means sustainable in terms of learning to live off the land and work on another planet. And I think those are the kinds of key lessons that you can't put in terms of a requirements document or anything, but that will really enable us to feed forward our what we've learned on the moon.
Great.
To Mars.
Thanks, Clive. Whoops, mute.
We need to utilize the resources on the moon and Mars. So we need to show that they're reserves by showing these are going to be enabling, in my opinion, for showing our decision makers that we have a tangible return on investment. That's very intricate, and there's a lot of things, as we found out in the Lunar ISRU workshop, that need to be developed, but we know what they are. And so I think that to me creates sustainability, so that there's not another 48, 50-year gap before we send humans beyond Earth orbit to explore other bodies, and we will then get to Mars in the 2030s, which hopefully I'll see, but we'll see about that. It's out of my hands. So
you'll see it. Thanks. That's great. Okay, Michelle.
I first started my career when we only had a single human spaceflight program in operation. That was the space shuttle. And as I was coming on board, Congress was just approving space stations. So then we had two flight programs in operation at the same time. And that was a handful. I think one of the most important things is if you look at everything we're doing now, we're still running the space station. We've got Orion and SLS going. We've got the commercial crew going. We're standing up the Gateway. We're standing up Artemis, and we're still talking about Mars. I mean, that is a lot of stuff.
A lot on the
so
plate.
Being able to put in place the right kind of contracts and mechanisms and public engagement and commercial engagement to be able that allows us to do that many different things all at once. I think that is that's pretty exciting right now. That we're not all focused on just one thing now. which is kind of fun at work because everybody's kind of got their own team now, and it's definitely been a little bit of a culture change when you don't have everyone all on just focused on a single mission or a single milestone. So that said, I want to go back on what Clive and Brett had said. So I 100% agree that sustainability is the goal, but historically in exploration, we don't build the plans for a city before we ever go visit it for the first time, right? We want to go scout a little bit, and to a large extent, the robots have done that. So that begs the question: do we only rely on robotic exploration to pick the site that we want to set up our sustainable base, and then the very first time humans ever actually set foot there is to build the city? Or do we do a little bit more scouting with the humans? That's a conversation that Clive and I will have beverages and debate late into the evening. A lot of different stakeholders have different perspectives on that, but I think that is an important conversation to have.
Great, thank you. Lisa, bring us home.
Okay, I will bring you home because we've been talking about sustainability, and I want to talk about extensibility, right? So everything that we're doing now, all of these programs are starting to, while there are a number of different programs, as Michelle pointed out, they're really starting to converge in terms of this one has to build on the one previous. And we have to take into consideration how something we're doing today is extensible to the next thing that helps us send humans further into the solar system and farther away from Earth. And so that extensibility is being built into everything we do. And I think that's as important as the sustainability. I like to tell folks, when you have no idea what you're doing, you start with what you know. And with every mission and every building block we have, we learn more. And that foundation of what we know gets greater and greater. And our ability to take that and extrapolate and adapt and develop systems to do something we've never done before, that is part of the magic of human spaceflight in general and aerospace, and the Artemis program giving us more knowledge, more things to build on. Mars Sample Return bringing us back more pieces of Mars and more information. Between those, we'll be able to start from a foundation and send humans farther with systems we haven't done before.
That's great. Hey, I want to thank all of you. This has been a wonderful panel, and thank you to all the sponsors and Explore Mars for doing this wonderful summit. We'll turn it back over to you. Thanks.